Hello, I'm DiNardo,
I'm Matt Jackson.
I'm Matthew Acosta.
and this is our group, and this is our project. This weight right here, we are pretending is a solid cylinder of mass 8 kilograms, and this is a cart, or really a longboard, that we're pretending is 3 kilograms.
All right, we are given a 240 millimeter rated cylinder that has a mass of 8 kilograms resting on a 3 kilogram carriage. The system is at rest initially when a force of P with a magnitude 10 newtons is applied for 1.2 seconds. In the first scenario, the force is applied to the carriage, and on the second scenario, the force is applied to the center of the cylinder. Now that we know that the cylinder rolls without slipping on the carriage, and we have to neglect the mass of the wheels on the carriage, we are asked to determine the resulting velocity of the carriage and the center of the cylinder for both scenarios. Action.
Alright, for all purposes right now, we are pretending that this is a solid cylinder, because obviously since it's not, its moment of inertia is different, but for our purposes we're going to pretend it is a solid cylinder. Alright, and here this is scenario 1 where the external force is being applied to the end of the board here, and it's not exactly going to be 10 newtons, but it's going to be enough to show us the motions of how the cylinder and the board would act. Alright, let me make sure we have it back here at the starting point. This is from the center of the wheel, and we're going to see how far the wheel moves and how far this cylinder moves. Sorry, just getting everything ready here. And okay, Matt, go ahead.
Alright, this is post-experiment, and now we're going to measure out the distances traveled for each of the objects. Our starting point was back on the table here
For cart B,
and ended at this point,
about 38 inches.
and now we're going to measure out where the cylinder traveled, how far the cylinder traveled. And now we'll measure out how far the cylinder traveled.
From this point here, which is approximately 13 inches.
As you can tell, the cart moved farther than the cylinder did in the same amount of time, meaning that the cart moved faster than the cylinder, which is very similar to our calculations. Now we'll perform experiment number 2 and scenario number 2, where the cylinder has the force being applied to it and not the cart. We know where the starting points of each object are, and we will see how far they travel in the same amount of time.
Alright, after performing scenario 2, we see that the cart moves about 14 inches, and the cylinder moves about 30. The initial assumptions for both scenarios are that the initial velocities and angular velocities are 0 because the system starts from rest. The cart B is in rectilinear translation, meaning that the velocity in the y direction is 0 and the angular velocity of the cart is 0. In cylinder A, we can assume that we use the relative velocity equation, so that VAX equals VBX plus omega across RAB, and that the velocity of the cylinder in the y direction is 0. The velocity of the point on the cylinder, which is touching the cart, is equal to the velocity of the entire cart, VBX.
In order to solve for VA and VB, we need to take the moments about C, which is a connecting point of the cylinder and the cart. This will put VA in terms of omega A, which is the first step in solving the problem. Next, we take the sum of the forces in the x direction, and this will put the forces in terms of VA and VB. Since we already know VA in terms of omega A, we can use relative velocity to put VB in terms of omega A and solve for omega A. Once we have omega, we can go back to the moment equation and use the solved omega to find VA. And finally, we can use relative velocity to solve for VB. From our theoretical data and our experimental data, everything seems to match up, and we assume that our calculations are correct. Thank you for your time.